First of all, thank you very much for giving me this opportunity. And let me again speak about spin-only talk. No itinerant electrons involved in my talk. So following a previous speaker, I'm going to speak about the materialization of a type spin liquid. Yeah, and this particular work was done in collaboration with those people listed here. In particular, Tomo Takayama and Kentaro Kitaga, those two are key players of this project. And so, sorry about repeating the same, but this quantum spin liquid has been some sort of holy grail in the field of quantum magnetism. And since Anderson proposed his kind of RVB model, the major playground used to be a geometrically frustrated spin-and-a-half Heisenberg magnet, like a triangular kagome. And let me correct the previous speaker a little bit. Anderson proposed this 15 years before HTC. Okay, so almost more than 40 years ago, Anderson proposed the concept of quantum spin liquid. And of course, ground state has been built to be some sort of quantum superposition of spin singlet. But as previous speaker emphasized, the ground state yet not yet obtained as exactly solvable state. Although theoretically it's not solvable, but experiment did a good job, and we have more than a few real material where we believe geometrically frustrated quantum spin liquid is realized. For example, those organic triangular magnet, you can see some signature of spin Fermi surface. Hypersymicite, that's kagome magnet. Again, you can see very likely quantum spin liquid behavior. But I'm not going to talk about RV-based spin liquid, but Kitaev spin liquid, which could be quite topological. And Kitaev brought some sort of fresh wave to the community of quantum magnetism. And as previous speaker emphasized, his model is quite simple. He placed spin-and-a-half moment on top of honeycomb lattice, and those spin-and-a-half moment are connected by ferromagnetic Ising bond. And you have three 120-degree bond in honeycomb lattice, and those bond Ising axis is x, y, g. So therefore, those three bond try to polarize spin for three orthogonal direction x, y, g. So therefore, this spin doesn't know where to orient. That's why frustration exists and the spin liquid is kind of realized. And again, as previous speaker mentioned, by introducing two kind of minor fermions, itinerant, localized, he said Ising-like, Majorana operators, he could obtain the ground state exactly, and it was quantum spin liquid. And we can expect two types of Majorana excitations in this Kitaev quantum spin liquid state. One is itinerant Majorana, behave like Dirac fermions, and the other is gap G2 flux excitation coming from localized Majorana. So here we have a kind of great opportunity to realize the Majorana fermions in real materials. Okay. But of course, Kitaev model relies on S equal 1/2 Ising. But in reality, it's not very easy to have Ising S equal 1/2. Okay, and you need some special ingredient. And it turned out my favorite correlated iridium oxide, which J1/2 pseudospin, provides a quite reasonable playground for this Kitaev model. And iridium 4+ oxide has 5d electrons. And if they are located inside the oxygen octahedra, okay, 16 oxygen around. Okay, so you have crystal field splitting between Eg and T2G, and you have 5 electrons in T2G. And iridium is a very heavy element, atomic number 77. So their atomic spin orbit coupling could be as large as 1 electron volt. So therefore, it's even larger than crystal field splitting. And as a result, the T2G orbital split into J equal 1/2 and 3/2. Okay, T2G is just like p orbital. However, sign is reversed, so you have J1/2 on top. Okay, and because of this, so you have 1 electron per orbital situation, and because of this, even with weak Coulomb U, the system can be Mott insulator. And of course, magnetic moment in the Mott state is J1/2 state, expressed by this formula. Okay, with equal superposition of xy, yg, and gx, and there is imaginary index I here representing orbital motion. So this is nothing but the spin orbital complex state with quantum phase. Now, as previous speaker mentioned, if iridium octahedra share edges, okay, like this way, okay, then you can have S equal 1/2 like Ising. Okay, the point is, you have 2 oxygen in between J1/2 moment, and so you can consider 2 super exchange paths. Okay, but J1/2 function has imaginary index I here, and because of this, those 2 paths experience some sort of a quantum interference, and as a result of interference, coupling is quite anisotropic, and only when moment are perpendicular to this plane, iridium oxygen plane, bonding in a plane, okay, you have ferromagnetic interaction. But the other direction, interaction is 0. Okay, so now using this J1 isospin, okay, it's equivalent to S equal 1/2. We have completely Ising ferro interaction, and this is essential ingredient to Kitaifu model. And in fact, as previous speaker mentioned, this specific compound, 213 iridate alpha type, you can see 2-dimensional honeycomb lattice of iridium oxygen octahedra. And as you can see from this figure, so you can see hexagon here. And those iridium oxygen octahedra are connected by edges. Okay? So you have a 290-degree bond, which gives rise to ferro-Ising interaction. And the octahedron has 3 orthogonal edges. Okay? So those 300-degree bond, okay, uses orthogonal 3 different edges. So they try to polarize isospins for x, y, g direction. Okay, this is nothing but the Kitaifu model. Okay, so this could be a beautiful materialization of the Kitaifu model. That's why people come to this compound. And in order to identify Kitaifu spin liquid, what we should look for. And as previous speaker mentioned, yeah, in some sense it's boring because we are looking for no magnetic order. The system should be paramagnetic. So we are looking for nothing, right? But I like it because I'm Japanese, and this Japanese Zen concept, we are looking for nothingness, and this is a typical Zen temple garden that represents nothingness. Okay, but of course, if you take a look at details, you can see topological pattern on top of those stone garden, and in fact, on top of nothingness, we have to find a hidden topological character there. That's what we'd like to do using a real material. And the people start looking for nothingness in the topological characters in a kind of compound purpose, like iridate and more recently ruthenium chloride. But as previous speaker emphasized, all compound people found magnetic ordering at low temperature. So we couldn't see nothingness. And besides, if you take a look at the Curie-Weiss constant, it's anti-ferromagnetic, not ferromagnetic. So that means on top of a Kitaifu type interaction expected, we have some additional anti-ferro interaction. And then people believe those additional interactions stabilize long-range ordered phase. However, we believe we are not far away from spin liquid phase. And we kind of look for some related compound. And we developed three-dimensional analog of 2D honeycomb lattice, which we named the hyper honeycomb lattice. Okay, so it's kind of three-dimensional lattice, but you have three equivalent 90-degree bond, exactly like a 2D honeycomb. So this actually you can build that 3D analog of honeycomb lattice, and theoretically you can expect spin liquid as well. But however, even in this three-dimensional version, you see clear signature magnetic ordering at low temperature. And again, we thought harmful non-Kita interaction killed the spin liquid in the state. So somehow, many of our colleagues in the community started giving up to find the real quantum spin liquid state, and they start looking for high energy signature of Kita F. Okay, but since I am a material person, so I couldn't satisfy this high energy signature. So we are still looking for quantum spin liquid at the ground state. Okay, we didn't give up. And we did many strange chemistry. And at the end of the day, it turned out by using soft chemistry, we can stabilize the quantum spin liquid state. So what we did was we started from this lithium iridate to the honeycomb, and using soft chemistry, we replaced all lithium in between honeycomb layer with hydrogen. Okay. This honeycomb plane we don't touch, but in between layer we replaced lithium with hydrogen 100%. Okay. And perhaps hydrogen gave some sort of strength and modified parameter a little bit. But somehow ground state seems to have changed drastically compared with lithium sodium compound. This is a basic characterization of our hydrogen compound, hydrogen honeycomb compound. And the first resistivity kind of insulating, indicating ground state is J1 Morton insulator. Susceptibility, if you subtract junk Q retail at low temperature, Q like increase and stay constant, go to finite value. And you don't see any signature of magnetic ordering. Specific heat, again, we don't see any signature of magnetic ordering. We are surprised, but somehow it looked like spin liquid. We seem to be seeing nothingness. But of course, susceptibility and specific heat is not very good proof to identify very weak ordering. So therefore, in order to identify nothingness associated with the liquid state, we went to NMR. Okay, so this is NMR spectrum for lithium and hydrogen proton. And if there were any magnetic ordering, those pixels split because of distribution of field, or at least broadened. But however, as you can see, okay, J is roughly 100K. So this is 1% of J, but you don't see any ordering in the peak, okay, like this. And we know, something like with precision of 10 to the minus 3 mu b, no magnetic ordering takes place in this compound, down to 1% of J. Okay, finally, we could have identified nothingness. Okay, this is kind of the strongest evidence, we have, nothingness and the spin liquid. And in fact, compared with, RVB type, perhaps RVB type, classical quantum, spin liquid, we found that this, compound is kind of cleanest. Okay, so although they say no magnetic ordering, but in reality, if you take a look at the low temperature NMR spectrum, you can see some broadening, meaning kind of slow, this fluctuation of a magnetic moment, at low temperatures. But our compound, compared with that, you don't see any broadening, down to very low temperature. So from the, line shape, we can say, our compound is kind of a cleanest, quantum spin leakage. And here is temperature dependence of night shift, which we obtained from NMO data. So this is some sort of intrinsic susceptibility without any impurity contribution. And again, at high temperature, you can see Curie-like, and have a broad peak, and go down, and the susceptibility stays constant over almost to the magnitude. Okay, that's quite impressive. And there seems to be finite magnetic susceptibility at t equals 0 limit. That might suggest we have gapless spin excitation. To kind of probe, to probe spin dynamics, we measured the spin relaxation rate T1. Okay, so this is 1 over T1T, which is essentially scaled by density of excitation. Okay, so in metals, there is a constant 1 over T1T that comes from density of states at Fermi level. And somehow 1 over T1T at low temperature behave like Fermi liquid metal. So you can see a constant 1 over T1T at low temperature. That means you have finite density of spin excitation. It's insulator. But if you take a look at low temperature behavior, you can see small downturn at 1 Tesla field. And at the beginning, I tried not to see it, but then my colleague started measuring higher field, and then actually with increasing field, this tendency of downturn gets clearer and clearer. So you can see downturn over 1 over T1T, with increasing field. Okay, and this downturn starts happening at like a 1K, 2K, 4K, 5K, 1 Tesla, 2 Tesla, 5 Tesla. So roughly, this happens of the order of mu BH, G-man energy. Right? And of course, this is nothing but density of state. So that means we have some sort of magnetic field induced gap in the excitation spectrum. And the magnitude of gap is roughly scaled by G-man energy. And suppose we have classical quantum spin liquid, RBB type. It's kind of singlet based. So therefore, if you do apply magnetic field, it should suppress singlet spin liquid state. But this case, you can see enhancement of gap. Okay, so that's kind of opposite. Okay, and we believe this is qualitatively different from so-called classical RBB type spin liquid. Okay, that's one thing. And second, those gapping is strongly field dependent. Okay, that you can see in T1T inverse. But if you go night shift, okay, they show different field, but you don't see any magnetic field dependence. So therefore, static susceptibility and dynamic susceptibility are very much different. So there is some sort of duality involved. And we suspect this could capture some sort of signature of exotic topological excitation we kind of expected at the beginning. And this gapping behavior under magnetic field you can see in the specific heat. Okay. Oh, this is a zero field specific heat down to 100 milli-K. And you can see weak increase of C over T. Okay, that's the kind of density of states, scaled by 1 over scale of T. So there seems to be kind of weak critically toward T equals 0. And once you apply field, you start seeing a drop of C over T. That means you are kind of gapping in excitation. Okay, again, it's of the order of mu BH. And in the gapped region, C over T is linear in T. Okay, that means we have a V-shaped gap, like 2D Dirac system. So we do see opening of a Dirac-like gap. And those, gapping behavior, we found there is beautiful scaling with, magnetic field divided by T over B. Okay, so this is a plot of T over P, and you can see both, specific heat and NMR T1 T inverse follows, similar scaling. That means we are taking a look at the same, bulk signal, okay, and clearly. And also this difference between specific heat and the T1, we can understand, from Fermi average. So the excitation should be ferromagnetic. So we are capturing some sort of ferromagnetic excitation, which exists in the bulb, the same signal. So we start capturing something unusual ferromagnetic, excitation. And let me tell a few things about the 1 over T1T. If you take a look at high temperature, so this is data for lithium, and this is data for hydrogen. And the hydrogen, you can see strong suppression with decreasing temperature, but hydrogen you see enhancement. So there is a kind of contrastive behavior. And this actually you can understand some sort of geometrical effect. It's called the structure factor, because lithium is located at the center of a honeycomb. So therefore, if there is anti-ferro correlation around the honeycomb link, it can be suppressed. Okay. But hydrogen is located on top of one specific bond. So they are sensitive to a nearest neighbor correlation. Okay. So that means ring correlation could be antiferromagnetic. However, those local interaction could be ferromagnetic. Okay. So that's kind of a consistent. Curie-wise is antiferro, but still type physics survives. And yeah, okay. So I have to. So this is almost last view graph. Recently, of course, the theory colleagues started collecting things, and this is one of the calculations done by Tokyo colleague Motome, and yeah, he calculated some dynamic properties, and he said this flux ordering, okay, this G2 flux ordering takes place something like 1% of J, so that's quite low. In our case, should be less than 1K. Okay, so the Dirac physics showed up, below 1K. Okay, but if I take a look at the specific heat above flux ordering temperature, like above 1K, they say we should see almost linear specific heat, like a metal, and that's what we observe. And as they say, at low temperature, you see specific anomaly associated with the flux ordering. And we see some weak anomaly, and which might be related to ordering of flux. Okay? And once we find those, somewhat similar physics here and there. Yeah, no, I'm done. So we kind of revisited this three-dimensional honeycomb, hyper honeycomb, and pressure it to control magnetic interactions. And we found that long-range magnetic ordering at 40K melts under high pressure, and they showed again spin liquid-like behavior. So quantum spin liquid-like behavior is here and there in iridium 4+ compound with this 90-degree bond. So I'm pretty sure they share the same physics. So in summary, so I think I could have convinced you. At least we have established that new cleanest quantum spin liquid. Okay, and I'm almost 99% sure we find a new quantum spin liquid. Of course, the question is whether this is really exact or not. And at the moment, I have to confess we have only indirect experimental evidence. Of course, we have to prove topological excitations. We see some smell of exotic excitations, like field index gapping, contrast between susceptibility 1 over T1T. And on top of it, from materials viewpoint, here and there spin liquid in iridium 4+, having a similar honeycomb-like structure. And I'm pretty sure that tells that this is kind of related to type physics. Okay, so thank you very much for attention.